to work on my on-off buttons here a little bit. One more thing, the mean and variance. So back to generic. We started generically. Look at the title here, although it's a bit grayish now. We started generally with random variables and their distributions, the discrete ones. Then we became specific, 3 specific. Now we get generic again, with a link to statistics and what we learned last time. Because last time we learned how to compute a sample mean and a sample variance for a column of data given to us from anywhere, from Excel or whatever. We have some data. We can compute the sample mean and sample variance to tell a summary statistical story about those data. Right? We didn't talk about probability theory at all last time. We just did those computations on the samples, and we explained, and I think most of us can get a feeling of what that means. Now today, we are going to learn something brand new and quite strong and abstract thing. That those concepts of mean and variance, they can be talked about and defined within the context of random systems or random variables, random phenomenon. And for instance, the mean of some random variable, the expected value also sometimes called, is given by the probability weighted average of all the possible outcomes. That's the definition of a mean. For instance, one throw with the dice, 1 to 6, fair dice, right? What's the expected value? What's the mean of a one throw, the random throw with the dice? Well, if I use my definition, I should collect all possible outcomes. That's 1 to 6. I should multiply each of them with the probability they occur. And then I should add all those things up. So I take each possible outcome times 1/6, add them up. In this case, it's of course just the average of the numbers 1 to 6, which is 3.5. Here's of course a little interesting thing about discrete situations. Would we expect most often to see the average outcome when we throw with the dice? No. We will never see the outcome 3.5, obviously, because it's the discrete outcome. But the 3.5 is what I think you all have a good feeling of, is the average we would see if we threw the dice 1,000,000 times. On average, if we collect the number and average all those numbers, 1,000,000 numbers, the average would be 3.5, right? I mean, this theoretical concept is telling us what the outcome of such a huge experiment would be. And that's also the understanding of this. Now it becomes a bit worse. Let me skip playing around with this. Let me not skip it. Let me play a little bit around. We can play around with this by doing what we did earlier. We can simulate 30 throws with a fair dice, and then we can see what the number is. Well, it distributes itself around 3.5. What if I put in equal 1,000? Do it up here. And I do it again and again. Because see what happened when I averaged 1,000 again and again, I get numbers quite close to 3.5 each time. This is actually sampling uncertainty that we will get back to in statistics in 2 weeks from now. So we can play around with these concepts. Yeah, this is the theory of what I was just illustrating. That if we really do it infinitely many times, it will be 3.5, right? So let's not dwell on that more. I just tried it. Here is we like to spend some minutes on this one. Here's an important concept. I already told you last time the variance is probably the most important concept of this course. Last time we did a sample variance. Today I'm defining the formal variability of a discrete random system by looking, like I did last time with real data, I'm looking at deviations from the mean. So I'm taking all possible deviations from the mean, and then I'm weighting with the probability that they can occur. And I square them like last time, and I add it up. This is a formula that matches our sample variance formula from last time. And to exemplify in the dice throw example, the mean of the dice throw, I already found that to be 3.5. So I used that. Then I could see 1 which deviates from 3.5 like this. I square it. I could see 2 that deviates like this. I square it. I add them all up. And here's a number that you might not have thought of before. The variance of a dice throw is almost 3. Did I bring? I didn't bring that. Let's just, what's the square root of 3? 1 point. Someone do that for me. I don't have to do it. 1.7. On average, that's the standard deviation now. On average, dice throws are 1.7 away from 3.5. Did you ever think of that? Next time you play dice with your mom and dad, you have the 1.7 card to play at a good time in the evening, right? And they will be impressed, I'm sure. You'll have to explain them what a standard deviation is, because maybe they wouldn't know. So we could also simulate that. I'll not do that now. Few slides at the end. This was the generic. We could define mean and variance. Here's the mean, here's the variance. For any density function, for any random phenomenon out there. Very generic concept. Now, it could be done for our 3 cases. And here comes the formulas. I don't prove them, but they're not extremely difficult to prove. With a little bit of math, you could prove that if I do this computation for a binomial and I do this computation for a binomial, these are the results I would get. The mean and the variance for the binomial. The mean, I think all of us would know. If I throw 10 times with a fair dice, I expect on average 5 outcomes, right? If I 10 times with a fair coin, no, I should. I would expect 5 heads out of 10 throws with a fair coin. We knew that. Probably this one we didn't know. And this one is going to be extremely important for doing statistical analysis of counts and proportions. A version of this formula is going to play a major role in doing stats on counts and proportions. You could find mean and variance for the hypergeometric. You can find mean and variance for the Poisson, which is beautifully simple. The mean and variance of the Poisson, well, the mean is not so surprising. That's the average rate. I basically already called it a mean, so it would be a bit odd if it wasn't a mean. But then actually the variance is the same number. How nice is that? That's basically it for today, but we're going to have a winner made. It's not going to be easy. Difficult question. Good job. Good job. Let's just do the heads thinking here as a final thing. There are 60,000 babies born roughly in Denmark each year, so on average that would be 50-50, more or less. 30,000 is expected. I wanted to write girls, but I had a limit on the number of characters, so I had to write boys because I was lacking one character to make it fit in. So we're talking about the boys. They are the successes here now. I didn't want it to be. 60,000, that's the end. The binomial formula, variance formula, as I told you, that was important. This is the binomial variance formula. 1/2 times 1/2, so 1/4 out of 60,000, that's 15,000. Then I take the square root of this number, square root of 15,000, and that's 122 roughly. That's pretty neat, right? So the average deviation from 30,000 boys or girls, would be the same, of course, is only from year to year. That's from year to year variability is only 122. It's pretty amazing, right? Very stable distribution of males and females from year to year in that setting. Good job, Falk. Falk, would you? I thought about last time, maybe I should give the offer to the winner to wave to us. So Falk, if you're here and you want, you can wave to us. Good job, Falk. Let's give him a hand. So thank you guys. Next week will be continuous distributions by Peter Bakker, because I will not be here, but he will do a brilliant job with you on doing the continuous distribution. So good luck out there.